And so if you're lucky, you can use this direct method. If you're not, you have to rely on something called Hess's law, which is an indirect method. Hess's law is an indirect method for obtaining enthalpy of reactions. Again, if we're lucky, the enthalpy of a reaction that we're looking for, we shoot for the enthalpy of reaction to be the enthalpy of formation. So if we take, so Hess's law states that it doesn't matter how the reactions proceed, as long as you get to the products that you want. So rather than thinking of a reaction in one step, you can think of a reaction as taking place in multiple steps. The sum of those enthalpy changes for each of the steps will equal the overall reaction. Another way of saying is that we can arrange and rearrange reactants such that we can build up unknown reactants. When reactants are converted to products, the change in enthalpy is the same regardless of the steps, whether they take place in 1 step or 1,000. So the total enthalpy change for a series of reactions will be the same as for the overall reaction. What do I mean by this? Right, A plus, oh, you guys love when I bring out the A's and B's. A plus B going to C. Let's call this delta H1. And then you have B plus C going to D. Delta H2. If you were to add these two reactions together, you would get A plus B plus B plus C going to C plus D. The sum of the enthalpies, H1, would be equal to this overall reaction. But things that are the same on both sides of the reaction cancel out, leaving us with A plus 2B going to D. A plus 2B going to D. With the overall reaction being equal to delta H1 plus delta H2. Now, it seems trivial, just adding reactions together, but there's actually other benefits to it. So, let's sketch one out. Carbon plus O2 to give us CO2. We know that there's a certain enthalpy associated with that. So we can think of this, if we think of this as a sort of a reaction coordinate where we graph the total energy, enthalpy. Carbon plus oxygen have a certain enthalpy, and then it drops down to just the CO2 and releases a bunch of heat. Now, you can do another reaction. We were curious on, well, the carbon going to 1/2 O2 to produce CO. We wanted to know what that one's enthalpy was. That's the enthalpy of formation of carbon monoxide. But you can't go out and measure it. But you can take carbon plus oxygen, CO2, carbon monoxide plus 1/2 O2 to give us CO2. Turns out that this delta H of this reaction, you can measure that, turns out to be negative 283 kilojoules. Now, not quite as good as the 393 of the carbon dioxide. So if we just do, we know that they both end at carbon dioxide, but if you just take O plus O2, 1/2 O2, you can see that this also releases a certain amount of heat. So, climbing the mountain climbing analogy. The carbon dioxide starts a little lower on the mountain, carbon monoxide starts a little lower on the mountain, progresses down to CO2, gets down there. But Hess's law says that, well, we can actually do reactions stepwise. If you take a look at this reaction, carbon plus 1/2 O2 going to CO, you'll see that they share common products and reactants. And there's a delta H associated with this, delta H forming of CO2, of CO, that we don't know. But these two reactions together, if you add them together, you get carbon plus 1/2 O2 plus CO plus 1/2 O2 going to CO plus CO2. And through the magic of cancellation, the carbon monoxide falls out, leaving us with carbon plus O2 going to CO2. Well, that is the delta H formation of CO2. What that means is the delta H formation of CO2 would be equivalent to the following. Adding these two reactions together. Delta H formation, the delta H of this reaction, delta H formation of CO, plus the delta H reaction for the combustion of CO in the presence of oxygen would be equal to the delta H formation of CO2. A known quantity we can measure, leaving us one unknown. So this gap right here would represent the delta H formation of carbon dioxide. And so what you'll find is that if you actually, you can use the implied information in known thermodynamic quantities to find unknown. In this case, the delta H formation of CO we can get from rearranging and solving this equation to give us 110.5 kilojoules.